We said that two events are independent when the outcome of one does not impact the probability of the other. So if we know one thing happens, it's not going to change the probability of the other one happening. There are the most common ways, the most common independent events that we tend to see are a die roll. If we roll two dice, if I tell you the outcome of the first one, it's not going to change the probabilities of the second. An example of things where they're not independent would be the outcome of the rolling those two dice and the sum of the two dice. So if I tell you the sum of the two dice, then that might tell you something about what you did or did not roll on the first die, let's say. So in any case, when we're talking about independent events, these three things are equivalent. So if we have any one of them, we know the other two as well. If you say that they're independent, this is the same as saying the probability of f given e is equal to the probability of f. So the probability of one event given that another one has happened, if it's the same as the probability of that event just in general, then you can say they're independent. And it doesn't matter if we say f given e equals the probability of f, or e given f is the probability of e. The important thing with this one is that this given f here doesn't change the probability, and that happens when they're independent. Another equivalent thing is that if the probability of the intersection of the two events is just equal to the product of their probabilities, their individual product, then that's another way of saying that they are independent. So like I said, if we have any one of these three conditions, we know that all three of them are true. Alright, so let's do an example. Suppose the probability of snow is 0.1 and the probability of a traffic jam is 0.8. The probability of snow or a traffic jam or both is 0.82. We're trying to figure out, are these events independent? Okay, so we're told, let's name some events. Let's call that S, and probability of a traffic jam, we'll call that T. The probability of snow or a traffic jam, this one is the probability of S union T. Notice I said union there because it's the first one or the second one or both. That gives me the probability of the union. If I'm trying to figure out if they're independent, you'll notice, I mean, there's a conditional probability in here. I don't really see how conditional probabilities would play into this. However, there is an intersection. This one talks about the intersection, the probability of the intersection of the two events. You may notice that I have the probability of S, which is 0.1. Maybe I should have said probability of T, which is 0.8. And I have the probability of the union. I have the three things necessary to find the probability of the intersection. So just a quick reminder here, the union rule says the probability of the union of two events is equal to the probability of the first plus the probability of the second minus the probability of their intersection. Through some quick algebraic manipulation, you could move things around so that you get the probability of the intersection is equal to the probability of the first plus the probability of the second minus the probability of their union. And this is the way I'm looking at it right here. I have the probability of the first, I have the probability of the second, I have the probability of the union. That's enough to tell me the probability of their intersection. So the probability of S intersect T is going to be 0.1 plus 0.8 minus 0.82. 0.1, 0.8 minus 0.82, which gives me 0.08. So to tell if these are independent events, is it true, is the probability of S intersect T equal to the probability of S times the probability of T. So like I said, I'm testing this condition right here. It says the probability of the intersection of the two is equal to the probability of the product of their probabilities. That's all I'm doing here. I'm saying, is this a true statement? And I'm checking this, so I'm going to do a question mark over it. So 0.08 equals, with a question mark, 0.1 times 0.8. Is that a true statement? Yes. 0.08 is equal to 0.1 times 0.8. We end up getting 0.08 for both of those. So yes, they are independent. Don't try to use your logic on these, especially if you're given these probabilities, because then you're more or less just guessing. This, like I said, this has nothing to do with causation. I said this in a previous video. It has nothing to do with causation, or frankly, I mean, there could very well be extenuating circumstances. If it's snowing, more people stay home, and thus there's less traffic, which perfectly counteracts the fact that there's the probability of there being a traffic jam. Who knows? So there's all sorts of different possible reasoning there. Don't try to rely on that reasoning unless it says, does it make sense for this to be the case? If you're given the numbers, use the numbers. All right, what is the probability of a traffic jam given that it's snowing? So what is the probability of a traffic jam? What is P of F given that it's snowing? What is the probability of T given S? Well, we just exactly concluded that these two events are independent, which means that we can use this probability, this line. The probability of F given E is just the probability of F. So the probability of T given S is just the probability of T. If these things are independent, that means knowing that it's snowing doesn't change the probability that there's going to be a traffic jam. We already found out, we were given the probability of there being a traffic jam as 0.8 right up above. So it's really not much to do there. The probability of T given S is 0.8. All right, I'm going to ignore that because I think it was written from a previous, yeah, whatever. All right, let's decide whether it makes sense for the following. So these ones, we can think through. We're not given specific numbers. So if E is the event that it rains more than 10 days in Chicago this month, and F is the event that it rains more than 15 days in Chicago this month, can these events be independent? So looking at the conditions for independence, there's really two of them. This is just the name, independence. If we know, the easiest way to think about these is if we know that it's rained 10 days, does that change the probability that it's rained more than 15 days? Or switch that around. If we know that it's rained more than 15 days in Chicago this month, does that change the probability it's rained more than 10 days this month? And yes, if it's rained more than 15 days, it's definitely rained more than 10 days, which means that these are not independent. The fact that this one has happened changes the probability of that one. The probability of F, the probability of E given F, I suppose. The probability that it's rained 10 days, more than 10 days, given that it's rained more than 15 days, is 1. And I mean, I guess we are using a little bit of an assumption here. I would assume that the probability of E is not 1 in general. It's not guaranteed to rain more than 10 days every single month. I suppose if it was, then you could say that those two were independent. A coin is flipped. E is the event that it's Tuesday, and F is the event that it comes up heads. Are these events independent? Well, I don't care if it's Tuesday or not. The probability of F, probability it comes up heads, given that it's Tuesday, is the same as the probability of F. It has no impact on the day of the week, has no impact on what this coin flip comes up as. So since this is true, these are independent. A card is drawn from a deck. G is the event that it's a face card. H is the event that it's a red card. Okay, so you could do a conditional probability here, I suppose. You can kind of, we have these two different ways that we could check for independence. Either of them work. So let's actually see if we could do both on this. So let's look at G given H compared to probability of G. So that's one way of looking at it. And then I'll do another way over here. So the probability of, what is the probability that it is a face card given that it's a red card? Well, the probability it's a face card given that it's a red card, we have 6 red face cards out of the 26 red cards. So the probability it is a face card, given that it's a red card, would be 6 out of 26. So given that it's a red card, that's the 26 there. And that it's a red face card, this is essentially what I'm doing here. I'm doing n of g intersect h over n of h. If you want to actually look to see what formula I'm using the size of the sample space, or I mean actually using my sample space here because it's easier than using the probabilities. And I could reduce this down to 3 over 13. The probability of g in general is, well, I would do the same sort of, well, actually in this case I guess it's just n of g over n of s. So that would give me the number of face cards is 12. The total number of cards on a deck is 52. If I divide both top and bottom by 3, I get 3 out of 13. And you can see they are the same, so we would conclude that these are independent. If we were to do this using the other rule would say compare probability of g intersect h compared to probability of g times the probability of h. So the probability of g intersect h, this is the probability that you draw a card that is face and a red card. Well, let's see, there are 6 out of the 52 cards in the deck are red face cards. I could reduce this down to 3 out of 26, I suppose. The probability of g, so the probability of a face card, is going to be 12 out of 52. And the probability of getting a red card is 1 out of 2. Or, well, you could write that in different ways. In any case, multiplying these together, actually there's a factor of 2 I could cancel, leaving a 6, giving us 6 out of 52, and you can already see it's the same thing. We get 3 out of 26. So, in both of these, we conclude that g and h are independent. Knowing that we're dealing with a red card has no impact on the probability that it is a face card. So these would be independent events. E is the event that it's Charlie's birthday. F is the event that it's John's birthday. If you know that it's Charlie's birthday, what's the probability it's John's birthday? Without knowing anything else, without knowing if they have the same birthday or different birthdays or anything like that, I would say it's perfectly logical to say that these are independent. With one additional caveat there. You could actually make the argument that these are not independent because birthdays tend to swell during certain times of the year, and if it's Charlie's birthday, then that means it's more likely to be during the high point of the year where you have more birthdays, which means it would also be more likely to be John's birthday. So you could make the argument, but it's a little bit more complicated to try to make that argument. I would say just in general, keep this simple. I would say that they're independent.